Good morning, everyone. Hi, how are you today? Cool. I'm glad all of you are waking up and had your coffee and were able to make it. So today I'm going to teach you how your packets flow, how networks on the internet work. My name is Leslie Carr, and I am a recovering network engineer. I'm currently working at Clover Health on the infrastructure engineering team. And I also am on the board of directors of a local nonprofit called the San Francisco Metropolitan Internet Exchange. And you'll be finding out what an internet exchange is later in the presentation. Previously, I've worked at a couple small websites you might have heard of, like Craigslist and Google and Twitter. So nowadays, a lot of you have switched to the cloud. So you don't really need to know how your networks work anymore, right? Amazon and Google all take care of that for us. But back in the old days, when I was a young network engineer, everything ran on physical hardware we had to manage ourselves. So we had to walk uphill both ways in the snow just to transmit a single packet. So today, I'm going to teach all of you how networks work both physically and how packets flow logically. So most of us know the basic theory. Here, a server is hosting a picture of my friend John's kitten. The kitten moves from one network to another and another. Eventually, I get my kitten fix. But those little networks are hiding a lot of complexity. First, let's talk about the physical side. We all know the internet is a series of tubes. So first, you'll have a rack full of servers. These are usually about 6 to 7 feet tall, or 2 meters for those of you who use real numbers. And those servers all aggregate to the network switch, which you can see there in the middle with all the cables sticking out. A network switch is a specialized piece of hardware, has a large number of network ports, as you can see. These network switches will all go up to an aggregation layer. This diagram sort of shows you what people were doing in the recent past, but you can still find this in many networks. Each rack switch would connect up to 2 to 4 core switches, or large centralized switches. On the good side, this kind of architecture is really easy to understand, right? Your traffic will go from switch 1 up to the core switch, back down to switch 2. On the bad side, those big expensive switches are really expensive. We're talking anywhere from $100,000 to $400,000 each. And they really limit network bandwidth because you only have those 1 or 2 paths. Nowadays, those middle switches are often replaced with what I like to call a redundant array of inexpensive switches, or CLOS. These cheap switches are usually in the $2,000 to $5,000 range. How CLOS is actually connected is incredibly complex, so buy a friendly network engineer or me a beer later tonight, and I can draw it out for you on a napkin. So we've moved to a model nowadays where servers tend to host a lot of VMs and bandwidth-heavy activity, right? Like kitten videos. So your home server, your home computer will probably have a 1 gigabit per second network card. But many servers nowadays have 10, 25, 40, or even 100 gig network cards. This is a picture of a 100 gig network card, and they're pretty commercially available nowadays. So I tend to find these numbers sometimes a little daunting, so I made a quick chart so you can see a sense of the scale of this bandwidth difference. So seeing the scale, 1 to 100 gigs, how do we manage to get all the data from one place to another without making this huge messy tangle of wires? The answer? Lasers. We use laser beams. With lasers, we can put a lot more bandwidth onto a single cable. So what we call optical networking is using a laser to shoot a single wavelength of light through a thin piece of fiberglass, as you can see here. Here is a very zoomed in picture of a fiber optic cable. You see that tiny little piece of glass there in the middle? It's anywhere from 8 to 100 micrometers. And then you see there's a lot of protective jackets around it. Because as you can imagine, with such a tiny little piece of glass, these cables can be very fragile. So let's go back to the picture from before. So you might notice in this picture, this laser light is also getting a lot dimmer as it's passing through. It's because every time you see the wave going up and down, some photons actually escape. So on the outside of the fiber cable, there's also a reflective coating we call cladding. It will reflect the light back down into the cable. So now that we know how this works, let's go back to the bandwidth chart. A single laser wavelength allows us to put about 200 gigabits per second onto a single cable. So this is pretty good if you see the scale chart. But as you can see, if you have a large rack of servers, 20 to 40 servers, they're each outputting kitten pictures to the internet, we'd still need a lot of cabling around the world. So we get around this using prisms. The core concept of optical networking works just like the cheap little prisms you remember from elementary school, right? Just in optical networking, since we like to have much fancier names, we call it wavelength division multiplexing. So it's a pretty simple idea. On the left-hand side, you have lasers all transmitting at a different frequency or color of light. It all goes to a mux, which is just a prism on the one side, transmits all through a single fiberglass cable. And then on the other side, the other prism we just call a demux, and it splits it all back out into each color or wavelength of light. So many modern optical systems can have 128 different colors or wavelengths of light, each at 200 gigabits per second. So that's over 25 terabits for a single cable. So now on a single tiny little strand, you can get a lot of data. So I also find terabits a little hard to comprehend. Let's go back to this chart for scale. Yeah, as you can see, look, like the carrying capacity of a single cable dwarfs anything a modern server can put out. And then on top of this huge bandwidth difference, the actual cable, remember, it's very, very tiny. It's only that tiny small piece of glass. Most of this width is from all the protective cladding. So since so much of this diameter is protection, you can put over 100 of those tiny little pieces of fiber into a single cable. That's how we avoid having all our street poles look like this. So you'll see 3 different flavors of fiber in the outside world, of how we get from one city or location to another. There's aerial, underground, and transoceanic. So first, over land is aerial fiber. You've probably all seen aerial fiber and haven't even realized it. It's strung up along poles, street poles, usually with electrical and telephone lines. The way that you can tell something is fiber is usually you'll see these loops and boxes for servicing. So on the plus side, aerial fiber is really cheap and easy to run and maintain, right? On the downside, it's exposed to the world, which can make it very prone to damage. Aerial fiber has 2 main natural enemies. Storms and people with guns. Storms, we've all had our power outages, right? During storms, we know how that works. So back in the old days when I worked at Google, we would often have a lot of outages at the beginning of bird season. So birds love to perch on wires. Hunters during bird season love to shoot the birds. They're not supposed to shoot at the wires, but as you can imagine, lots of shotgun-related outages. Yeah, seriously. So how can we protect all of this very fragile fiber? Underground fiber is much safer and more protected. You just dig a trench, just like you would for your sewer pipes, or some electrical cables are also being put underground now. On the downside, digging those trenches can be very expensive. Plus, whenever there's damage or repairs needed, you have to dig the whole area up again. So that also makes the repair side more expensive, even though it's much more rare. And underground fiber isn't immune from its own natural predators. Careless utility workers. Oh yeah, backhoes digging where they're not supposed to be is #1 predator of underground fiber. So now we've seen the first two types of fiber over land, but oceans are 71% of the Earth's area. And we all know we don't want to have a North American internet, a European internet. That would just be sad. And the European one would be so much classier than ours. So, undersea or transoceanic fiber. This is the actual map of all of the undersea fiber cables in the world. So if your traffic is leaving the continent, it's going over one of these cables. It's actually laid down by boats. This is a fiber laying boat. They have these huge spools and they slowly go across the ocean, spooling out incredibly long fiber runs. They're super large and super awesome. So, of course, there's natural predators for undersea fiber as well. The biggest one are boats. Boat anchors can easily snag and drag and break these fibers. It has happened a lot. So if you see a sign that says, "Don't put your boat anchor down," I'm looking at you. Don't do it. As well, even scarier, sharks. Yeah. That is a shark actually biting a cable. We aren't quite sure why sharks like to bite cables, but I don't know. I'm not asking that shark. That's scary. Yeah. So yeah. You might notice there's also comparatively few paths to a couple places like Australia, which explains why sometimes getting network connectivity there can be rough. And also, there's relatively few endpoints in some regions. If you see right there, Hong Kong, so earthquakes or a boat anchor can actually take out a large number of undersea cables in a single swoop, which can lead to network difficulties in an amazingly large portion of the world from one small event. So now we know how the traffic physically moves from one place to the other, but how does it know where to go and get delivered? Network traffic transits the world in what we call packets. When a computer wants to transmit a kitten file, it'll cut it into smaller chunks. A packet's usually about 1,500 bytes. It will put a header onto the front. Now, I know this header looks like a lot of complex information, but you don't need to know most of these fields right now. What you do need to know is the destination address. Network switches will look at this destination address piece of the header to determine where the packet needs to be sent. Even when you encrypt your data, these headers will stay unencrypted so that your network knows where to deliver its information. So now your switch knows where you want to send it, but how does the data know how to send it? How does it know where to put it? Switches know where to send packets using something we call routing tables. A routing table is just a very large lookup table where the switch looks where do you send the packet next in order to get to its destination. You may also have heard of the term routers. Historically, there were a lot of difference between switches and routers, but not anymore. Nowadays, the only real difference is that a switch is cheap and will have a small routing table, and a router is very expensive and has a large routing table. So let's go back to the kitten pictures and see an example now that we know what routing tables are from before. I'm asking the server for my kitten fix, giving it my IP. So the server does a lookup in its routing table to discover which interface to send the kitten picture out of. This one says, oh, I know, that goes out interface 1. Passes it to the next switch. The next switch says, I know how to get there, interface 4, and so on. And then the kitten's delivered. Here's what a very tiny piece of an actual routing table looks like. So the current number of entries just for IPv4 on the internet for the routing table is over 650,000, and it is growing every day. So I obviously couldn't show you the entire one. It would take up all the slides. So now we know how the switches and routers know where to send the packets. But how do they get those connections to their interfaces in the first place? The first way is something we call transit. Transit is like an internet service provider for your internet service provider. So at your house, you might have Comcast or Monkey Brains or Verizon, and those internet service providers will have someone like Level 3 or Zayo. So transit providers are just your ISP for your ISP, which is pretty cool. But transit providers, being businesses themselves, also charge money. So in the kitten picture for before, the kitten server goes via their transit provider, which charges them money, goes to another transit provider, and then my home ISP also pays their transit provider money. So there's some costs for both providers. These costs can really start to add up. Also, on top of the costs, if your kitten server and your ISP are in the same data center, you're adding a lot of extra hops and extra places. You might have to go out to another building and back in. So those extra hops can add extra time, what we call latency. So this could have a suboptimal user experience as well. So we solve this with something we call peering. Yeah. The first type of peering is called private peering, and that's when two networks will directly link to each other. So if the kitten ISP and my ISP have a private peering link, network traffic goes directly over the connection, right? Which is pretty great. Both sides save money. I get a better kitten experience because there's less latency. So do you think that everyone in a single building does that? Obviously no, or else I wouldn't be asking this question. Switch and router ports can be very expensive. And so if you can have 100 or so networks in a single building. So you would need a lot of very expensive switch ports as well. You can't just throw a cable from one rack to another. It would get crazy messy. Seriously, that's real. It's horrible. Data centers insist that they get to neatly run a connection, and they call it a cross-connect. These cross-connects usually meet in a single room called a meet-me room. This is one of my favorites. It's in Seattle, and they've done a beautiful job. These cross-connects, depending on who your data center provider is and how good of negotiators you have, can cost anywhere from $300 for a one-time fee up to about $400 every month. So it can be worth it if you're doing a lot of traffic between a network. But depending on the cost of this, $300 a month times 100 different connections can really start to add up. So we might not want to throw, on top of the cost of the router ports, we might not want to throw cable directly to every other network. So how do we deal with this problem? Internet exchanges or peering exchanges. With a peering exchange, many networks will come together and agree to connect to a single provider called the exchange. This way, if you want to access all the 100 networks in a single building, you only will need one cross-connect and one router port. So you get a lot of those benefits of peering without as many of the drawbacks. Then you only have to pay your peering exchange provider. So this costs a lot less than your transit connection does because the peering exchange only needs to have access between a single building or maybe a few buildings in a little area, and they don't need to let you know how to get to the internet as a whole. Peering exchanges also have a wide range. They can range from small nonprofits like SREcon17 or Seattle Internet Exchange, whose router you just saw previously, to large multinational companies like USENIX, who run these around the world. So in the real world, companies' network would use a blend of transit, private peering, and internet exchanges, all based on costs, where they're physically located, and latency, to ensure that you have a really good experience for all of the end users. Now you know how the internet works. Any questions? Oh, if you do, please go up to the mic so that remote listeners and recorded people can hear your question.
Hello. So, a little obscure. What's the I at the end of the AS numbers in the big wall of
Oh, I didn't explain BGP, which is the protocol that sort of tells routing tables how to get to the place. And so the I just is internal BGP marker for, so it's called internal for a route marker. It's a weird, obscure thing that is not very important, but I could have another 25 minutes on just BGP alone.
So beer.
So beer, yes.
Cool.
Beer.
Thank you. Hello.
Hello.
Nice presentation. Thank
Thank
you
you.
for doing it. I had a kind of off-the-topic question because the other day I had to help a developer troubleshoot a flannel issue in Kubernetes. So I'm curious, for someone like me who's basically a sysadmin, what are some good network topics to know now that we're going to have to do more things with containers and know more about the networking layer?
That's a tough question. Yeah, so for containers and networking, well, I mean, honestly, my favorite tool is always just start with ping because that's how you figure out about that. Man, I mean, it can be so difficult because a lot of times you have an overlay network. An overlay network is like a virtual network, so that all the containers will be running on. Are you running your own physical hardware? Or,
yes, we have our own cloud.
Okay, like are you using like VX? So a lot of people to transmit that information will use VXLAN, which might be another good topic for you to research.
I guess the question is more like,
Sorry.
I understand the protocols, like I've heard of BGP and stuff like that, but I'm not a network engineer. We have a networking team, but it's not going to be efficient for me to go to them whenever I have to troubleshoot like a container issue. So like, what are some basic things that a sysadmin could know that would help us now that we have to do more networking?
Yeah, so really the basic thing, figuring out how you can do connectivity checking, which would be ARP tables and pings. Basic firewalls as well. I don't know if you're using IP tables. I know with containers that can really mask all of those things because you don't necessarily have because you're inside the container doesn't understand all the external issues. So I would definitely check out those.
Thank you.
To start. Thanks. All right. One quick question. Yes. All right, and I think these will be the last questions.
So if you can fit like 25 terabytes over one fiber connection, I mean, I don't know what the current like long haul bandwidth is, but it seems like bandwidth is basically free. Why is it so expensive still?
Yes and no. There are many reasons. One is there is some semi-monopoly. Another is in between continents. These systems were put in place a long time ago, so they don't necessarily have the capacity that the modern systems have. As well, building new fiber connections can be very expensive, as well as also just monopoly pressures. All right, last question.
So how do we take it beyond the basics then? So from a software engineer moving into an SRE role where we're going to know more network engineering concepts, where would you send us then to take these basic concepts that you've given in the talk and
Well,
dive
Julia
deeper?
Evans wrote a really great zine about networking right out there, which is a great place.
I haven't read it yet.
Go read it. It's really cool. Also, NANOG is another conference for network engineers, and they have most of their talks online. So it's another great place to go look for some basic information on getting started on this topic. Thank you.